You know, when you use an app like Netflix or Google, you're actually talking to a system of thousands, maybe even millions of tiny services all communicating instantly. So how do they pull that off without the whole thing just collapsing? Well, a huge piece of that puzzle is a technology called gRPC, and we're about to pull back the curtain on exactly how it works. So here's our game plan for this explainer. First, we'll nail down the core communication problem that every single microservice architecture has to solve. Then we'll see how gRPC swoops in to tackle this, first by delivering mind-blowing speed, and second by enforcing some serious safety. After that, we'll see how all the pieces click together, and finally we'll zoom out to the senior engineer's perspective to really understand the critical trade-offs you're making when you decide to use it.
All right, so let's set the stage. We build modern software out of these small, independent services. But this immediately creates a brand new fundamental challenge. How do we get all of these different pieces to talk to each other reliably?
This all boils down to a concept called inter-process communication, or IPC for short. You can just think of it as the rulebook that allows two totally separate programs, even programs written in different languages, running on completely different computers, to exchange information over a network. Okay, to really get this, let's think about a restaurant. A monolith is like one single chef in a kitchen. If they need to pass an ingredient from one hand to the other, it's instant. But microservices? That's like having a bunch of specialized chefs, each in their own separate room. To get ingredients from the prep station over to the grill now requires a runner, and that runner is our network.
See, this is what it looks like in that old monolithic world. Everything's in the same program, sharing the same memory. So when you call a function like process order, it's just a direct jump in memory. It is, for all intents and purposes, instantaneous. But now, with microservices, that exact same goal becomes this whole song and dance. The process order remote function has to do a bunch of steps. It's got to pack up the data, send it across the network, sit there and wait for a response, and then unpack that response. This is absolutely not a simple in-memory thing anymore.
And this right here, this brings us to our first really critical senior-level insight. The number one rule of distributed systems is that the network is fundamentally unreliable. A local function call, it only fails if your entire program crashes. But a remote call, oh man, it can fail for 1,000 different reasons that have nothing to do with your code. A network cable gets cut, a router goes down, someone adds a new firewall rule. Treating these two types of calls the same is a recipe for disaster. So we've established that this communication is tricky and it's unreliable. Now for the next question, how do we make it fast? gRPC's first big promise is a massive, massive improvement in speed. Picture it like this. Using something like REST with JSON is like sending a package with a long descriptive letter inside. It's really easy for a person to open it up and read it, but a machine has to painstakingly parse the whole thing. gRPC, on the other hand, is like slapping a barcode on that package. A human can't read it, but a machine. It can scan it instantly and know exactly what to do. So let's really dig into why REST, which is fantastic for web browsers talking to servers, becomes a real bottleneck for server-to-server chatter. First, it uses bulky JSON text. It's built on an older text-based protocol. It can get stuck in these little traffic jams because of something called head-of-line blocking, and it forces every single system along the way to waste precious time just parsing text. And now look at gRPC. It's like it was designed to fix every single one of those problems. It uses protocol buffers, which is a super efficient binary format. It runs on the modern HTTP2 protocol, which also speaks in binary. It supports something called multiplexing, which gets rid of those traffic jams. And it completely skips that slow text parsing step. It is built from the ground up for pure machine-to-machine speed. But, and this is a huge but, here's the trade-off. That barcode is completely unreadable to you and me. When something breaks in production, you can't just curl an endpoint and see a nice, clean JSON response. The data on the wire literally looks like garbage. A senior engineer knows that you absolutely must invest in special tools like gRP curl just to make debugging possible. You are actively trading away easy debugging for raw performance. Okay, speed is one thing, but what good is speed if your services are just shouting nonsense at each other? The second pillar of gRPC is safety, and it achieves that by enforcing a super strict contract between services. This right here is the blueprint. It's a file that ends in .proto, and it is the single source of truth for communication. It defines exactly what services exist, like product info, what methods they have, like add product, and precisely what the data structures look like. There is zero ambiguity. It's like an architectural plan for communication.
Now, you might have noticed these numbers, the equals 1 and equals 2. You might think they're for ordering the fields, but nope. They are way more important than that. They are permanent, unique tags that are used in the binary format. This is the secret sauce for backward compatibility. It means you can add new fields with new numbers, and old clients will just ignore them. But if you ever change or reuse a tag, you break everything. All right, so we have this perfect blueprint. It's crystal clear. But that leads to a pretty big question. Who actually sits down and writes all of that tedious, error-prone code for packing and sending and unpacking all this data? Before we get to the answer, we need another dose of reality from the senior perspective. This blueprint gives you safety, sure, but it also gives you rigidity. If you carelessly change a field's type, say from a string to a number, and you deploy that new server, every single old client that tries to talk to it will instantly crash. You have to treat this contract with extreme care and have a solid strategy for evolving it safely. Okay, so let's connect the dots. Let's see how this blueprint magically transforms into actual working code that does all the messy network stuff for us. Okay, take a look at this. This slide lays out the entire workflow, and it's beautiful. At the very top, we have our single source of truth, that productinfo.proto file. We then feed this file into a special compiler, and poof, it automatically generates code for us. For our Java client on the left, it creates what's called a client stub. And for our Go server on the right, it creates a server skeleton. These generated pieces handle all the complicated networking for us. You know, I think the best way to wrap your head around this is to think about a universal remote. The client stub is the remote in your hand. You just press a button on it. It feels like calling a local function. You don't know or care about the infrared signals it's sending out. The server skeleton, then, is the little sensor on the TV. It receives those signals, decodes them, and tells the TV what to do. The developer just has to write the TV's logic, not the sensors. And this is the payoff. Look at this server code. The developer isn't writing any networking code. They're not writing any serialization code. They just have to implement the add product function and fill it with their business logic. All that complexity is just hidden away by the auto-generated skeleton. It's a massive, massive productivity boost. Okay, we've seen the nuts and bolts. Let's pull way back now and consolidate all those key trade-offs that a senior engineer is constantly thinking about when they're deciding whether or not to use gRPC.
This is what I like to call the senior engineer's reality check. These are the things you have to accept. First, networks fail, period. gRPC doesn't change that fundamental law of physics. Second, you are making a conscious decision to trade easy debugging for raw performance. Third, that rigid contract means backward compatibility isn't a nice-to-have, it is a discipline you must enforce. And finally, because the stub makes remote calls look so deceptively simple, it's dangerously easy to create performance nightmares, like putting a network call inside a loop.
Which leaves us with the final question, the one you have to answer for yourself. gRPC is incredibly powerful. It offers amazing speed and type safety, but it's really designed for that internal server-to-server communication. And it comes at the cost of complexity, rigidity, and a much steeper learning curve. So looking at all the evidence, you have to ask, for your specific project, are those benefits really worth the trade-offs?